Thanks for giving me your full attention today. If you've just gone to the second keynote, the afternoon keynote, you might have heard mentioned, I was there at the beginning, but eventually I left to get ready. You might have heard mentioned LWJGL during this talk as a gaming library that allows you to program video games in Java. What that is doing under the hood, that library, I just thought it's interesting to share, is essentially what I'll be talking about today. But of course, it's much more broadly applicable than just that. But I thought because it kind of resonates with that, it would be interesting to mention. And of course, the topic that I will be talking about today is the foreign function and memory API inside of Java. Because impossible in Java, think again. Using the brand new foreign function and memory API in Java, you can have full access to the entire native landscape of interfaces, libraries, and drivers that is so prominent in languages like Python, and that's what makes it so powerful. This used to be possible in Java already, but it was difficult, and now it's been made so much easier with one of the brand new innovations inside of Java, and I think the most exciting new feature. I'll start with a little introduction. My name is Lennart ten Wolde. I am a software engineer at Chillit. You might have seen us as well at the keynote session. You saw the co-founder John there today. And I'm also here today because I like sharing knowledge. I'm passionate about Java, and I always feel like when I'm experimenting with something new that this is very exciting, and I just really want to share it with people. So that's what we're doing here today. Chillit is a sponsor at the conference today. We have a stand, and we're just here because we really like programming. We're passionate about sharing it. We're a company that's entirely ran by programmers. Up to the very top, our founders are also programmers. And we're passionate about knowledge sharing, which is why we're here today. I was here last year as well, so maybe you recognize me, but even if you don't, I hope you'll have a good time today learning about this exciting new feature. So obviously, I've mentioned already that the topic today is the Java Foreign Function and Memory API. But what does that mean? What can you do with this API that is brand new in Java? Well, you can use this to call foreign functions, which just means functions inside of another programming language, using a C-compatible interface, which are called opcalls, because you're calling up to another language. But this includes the operating system itself, the native platform, because most operating systems are built from the ground up by implementing the C standard library, and they extend this with custom features, drivers, and access to certain hardware features. And because Java has such an extreme focus on cross-platform functionality, not everything that is in your platform, in particular when it comes to hardware, is available to you in Java, because Java is supposed to be uniform and run everywhere. So using the foreign function memory API, you can access these things anyway. And also, using the foreign function memory API, you can create callbacks that can be passed to native functions that can then call back into the Java landscape and run your code. So your own code, your own methods can be triggered from native code by passing it as a callback. These are called down calls because the operating system calls down back to Java. And of course, the memory part of the memory API means that you can also manage native memory from inside of Java. So this means that you're just given a block of memory, which, contrary to Java, where everything is managed in objects and you don't really know what happens to an object, where it's located, where it's going to be located, this API just gives you full access to control memory in the way that you see fit, to the exact same degree that you would in a native platform. It's extremely powerful and fast, and is, of course, an absolute requirement for being able to interact with native code. So why am I talking about it today? Why do I think it's interesting for everybody here? And I truly think it is. Well, first of all, historically, this was already possible in Java, using the Java native interface. But this is back from the Java 1.1 era, and that's pretty old, and it shows. you had to write manual glue code, so this is native C or C++ code yourself, to kind of tie the Java landscape and the native landscape together. And this was a bit of a pain, because you now have to compile these, so you need 2 separate tool chains. And it was just a bit of a headache, because you have to learn a second programming language as well, which maybe you don't want to. You just want to use a library because you think the library is exciting. Also, I think it's exciting to talk about this because there's so much more demand for native interoperability today. I already mentioned how popular Python has gotten, and one of the reasons for that is how easy it is in Python to get full access to and take full advantage of the native libraries in the platform. So you can use this for accessing hardware accelerated features on your system because it's highly specific to the current platform you're running on. Java is not going to make this available to you by itself. So if you need hardware accelerated access for cryptography, high performance computing, or multimedia processing, artificial intelligence, or machine learning, you can do that using the Foreign Function and Memory API. On top of that, you can integrate with the very operating system itself, which exposes interfaces as an extension of the C standard library. So everything that is highly specific to your current operating system, whether it be Linux or Mac or Windows, you can access using these native interfaces in Java just as if you're writing actual native code. But also drivers. A lot of special hardware has proprietary drivers like graphics cards, but also highly specialized devices, and have access to optimized networking routines that are not exactly cross-platform, but allow you to extract more performance out of your networking code, are just some of the examples. And to kind of summarize all of this, ultimately, as it is explained in the enhancement proposal that brought about this new API, Java developers should have a supported API that enables them to straightforwardly consume any native library deemed useful for a particular task without the tedious glue and clunkiness of JNI. So let me talk about that really briefly, because I mentioned JNI a couple times. And just to give you an idea, this is where we were just a couple of years ago. What you would traditionally do is it would work from Java code first. So you have some regular Java code, and then you have a native method. If you've ever looked at the JDK source code, you've seen these a whole bunch of times. It's essentially the same idea. You define kind of an interface in Java, and some native code has to do the complete implementation of this message, and you can just pass in regular Java objects. But that means that you cannot directly use this to call into native code because you're passing in Java objects, which are not compatible with how native libraries work. So what you would do for this native method to get it to work, you always have to write some native code, because if you run it, you get an unsatisfied link error saying, hey, there's this native method, but I don't have a backing implementation, so it doesn't work. And then what you have to do is in the Java compiler, you can specify an extra option to tell it where to put a header, which is a C or C++ file that you need to implement yourself in C or C++ to make the functionality possible. So it can look just like that. You tell it, hey, just put it in my root, so pass dot as the location for the header file, and then give it your Java file where the native method is. And it generates something like this. You don't really have to know what all of this means, also because I would consider this to be legacy at this point. And the important part is it generates some native function definition, and it looks complicated, even to me, which you have to implement yourself. And you then have to work with this JNI environment and JObjects and JStrings in order to read information from the Java landscape and convert that to native code. Not only is that slower, but it's also just a massive pain as a Java developer, and which is why I never actually used it. So why is JNI clunky? Well, you have to define native methods in Java, and then you have to generate a C or C++ header. You need to implement some C or C++ code that interacts with the Java objects and actually does the native calls that you want to do. They need to compile and distribute your own compiled glue code, and you need to do that for each architecture separately. It's just a lot of pain, and then you need to load this at runtime, and then you can finally use it. But this is not very fun. So Java FFI API tried to reimagine this in a more modern and Java-friendly way that adheres closer to the way Java works. So Java FFI API is a full programmatic interface for native interop, which means that you're just programming regular Java code, and you'll see it's really not difficult at all. You obtain a linker, which is an interface which you can use to access native foreign functions on the current platform. This is a term used in native functionality because you're linking to external code. With this linker, you can find, using the symbol name, which is just a function name on the native platform, which can be any language, including Rust, for example. You pass the name and it finds where the function is, and then you can use it. You can then, from the linker, create method handles. That's a pre-existing Java feature that allows you to invoke functionality dynamically. Think it's like a somewhat more modern alternative to the standard reflection API. You can create a method handle and then you can invoke it. It's part of standard Java. So you can create these method handles not to call into Java code, but to call into native code. And it works exactly the same way. You can also create your callbacks from here to call back up to Java. So these will be your opcalls. Okay, so what does that look like? Well, this is a very basic example where I'm going to show you just how easy it is to get started. So first you need a linker. There's a static function called native linker, which passes you a global linker that links to the native platform. You take this, and then you want to use some functionality from the standard library. So you need to know where to look for methods. And if you use default lookup, then you have access to all of the libraries installed in standard locations on your platform, which will include the C standard library. And my father once gave me a book, which was the original ANSI C Bible. And it had in it explanations for all the different standard C functions. And one of them is called rand, which returns a random number. Now, it's a very simple function, which makes it good for a basic example. So what we have to do, sorry, let me go up one more time, is in our symbol lookup, which just looks up for any standard location installed library, we can say, okay, look for a function with the name rand. And every function name must be unique, so you don't have to tell it what the signature looks like, just the name. This gives you a memory segment, which is just a pointer to some space in memory. It's not exactly like a native pointer because Java allows you to specify the format, the structure of this memory as well to make it safe to access, so it can check you're not going out of bounds. But essentially, a memory segment is a reference to some area in native memory that's not managed by Java's heap, which means the garbage collector does not manage this memory, it won't relocate it, which is required to be able to pass these pointers to native memory. So you get the location of where the random function is in memory. You then create one of these method handles. Again, method handle is not part of the FFI API, it's standard Java. You create a down call, you pass in the address of the function that you just located, and then you have to pass a function descriptor to describe what this function looks like. So in this case, the random function returns an int, doesn't take any parameters. So pretty simple example, we start with the return type in the function descriptor and then the parameter types. But since there are no parameters, that's it. And then you can just .invoke to invoke this native function. And if you run this, believe it or not, it will output this number. Not always, because it is a random number, but a very small chance that you will get the same output. And what you'll see in here as well is if you don't want to get a warning about using native functionality in your code, you have to specifically enable it in the module where you're using it. So if you're not using Java modules, you just pass in all unnamed like this. Otherwise, you get a warning. This is the same in JNI. Java wants to eventually make it so that by default, you cannot use native functionality, not because they want to discourage developers from using it, but because they want the developer to very intentionally access native memory and not accidentally have a library that does this without the developer knowing about it, and because it does raise some security concerns. So let's do a slightly more complicated example, and then I promise we'll get to the really interesting stuff with some practical use cases. So there's another function in the standard library called divide, but the divide function that can do a division can return both the quotient and the remainder of a division output. So normally, if you want to get the quotient, you have to do a modulo operation, and if you want to get the remainder, and if you want to get the quotient, you have to do a divide. So to do this in Java, you would need to do 2 divide operations. In C, you can do this with 1. But let's say we really want to do it with a single divide instruction, then we can use this C method. So this time, this actually returns a struct, which is an output that's like, some languages have these tuples where you return like kind of multiple fields. Java doesn't support this. It's either an object or it's a primitive. But in this case, it returns a struct, so we have to define what that struct looks like so we can access it safely. So it just has 1 integer for the quotient, 1 integer for the remainder. And then we can say that instead of returning an int, it now returns this custom type, and it takes 2 integers as parameters. So, fair enough. Now when we invoke it, we have to pass these numbers, and you'll see here there's arena of auto. That's related to memory management. Essentially, because Java doesn't support returning compound values, only primitives or objects or pointers, it cannot give you 2 integers separately and you can store it inside of a single variable. So instead, it's going to put it somewhere in native memory for you, and you have to tell it where to put these fields in native memory. So you need to pass it an allocator. Here we passed auto. I'll get back to that later, but that's why that's there. And now, if you read the first and second value, which would be the quotient or remainder, and you can also access them by name, but this is faster, and you run this, you will get an output that 31 divided by 10 is equal to 3 with a remainder of 1. And this will only perform a single CPU instruction, and it will use the divide operator from C. Again, Java probably would optimize it if you did this in 2 separate divide operations in Java, but it's a good illustration, I think. But I'll stop with the simple examples, and we'll get to an upcall example. So what if you want the native code to call back to your Java code? So you don't want to call a native function from your operating system. You want the operating system to call back to you. Well, there's a function called quicksort, which sorts some data, and then in order to perform the sort, it has to do a comparison, right? I assume most of us have written a simple comparison function in Java. In C, you have the same thing. So this is a callback where you have to specify how 2 items are compared so it knows how to order them. Well, how can we pass something to there that will call back to our Java code? Well, we do so with an upcall. So let's say we have this static function, which I've called sort, but this is really our comparator function, and it takes 2 areas in memory and it has to compare them. Well, let's say they're all just integers, and we just want to order these integers in an, I believe, ascending fashion. Then what we can do is we can read the integers at these memory locations and subtract them, and then we just return this from our comparator function. Again, very simple example, but if you want to sort a list of integers and all of those integers are in memory, this is how you would do it. So to pass it, we find the qsort function, and we create a down call handle like usual, and you see here the last parameter that we pass is an address, and that's the address to our comparator function. But how do we get this address? Well, the upcall stub creates some native memory that calls into your Java memory. So it returns another memory segment, and you can then pass this as a callback function to any functions that want it. So in this case, we just use the method handles API, standard Java. You can also use reflection to achieve the same thing. Doesn't really matter. And we find a reference to our sort function. That's pretty standard. And then we have to give a function description of how the native function would look. So this function returns an integer and accepts an address that points to memory that contains an integer. So that's what with target layout does. And then if we try to read more than a single integer, we'll get an exception because we specified that this memory only contains one single integer. So if we try to read a long or we try to read two integers, Java gives us an error because we're reaching into memory that we shouldn't be looking at. So it's an extra safety feature. But we specify the signature, and finally we tell it where it should put the generated native code that calls into our Java code. And again, I'm specifying auto. So automatically manage this memory. Well, then we need to create some native memory to sort. So we just have a set of integers that we're going to put somewhere in native memory. Again, auto manage the memory. We have an unsorted list of numbers. Then we pass this with our callback, and we say there's 5 entries in here. They're each 4 bytes, which is the byte size of a single integer, and compare them using our custom callback. And if you run this, and then you take the output, or the memory that's now been sorted, we copy it back into the Java landscape by doing toArray Java int, which just returns an array of integers. We get a sorted array of integers, and it outputs 1, 2, 3, 4, 5. So this is how you can call in the native code calls back into you, and you have full control over the native memory. So I touched a little bit on native memory management, but how does it work exactly? This off auto thing was kind of strange. So let's talk about that briefly, and then I'll show you some cool examples after you understand all of the building blocks and fundamentals. So a memory segment is a bounded pointer to RAM. That means that you just have a segment, literally, of memory which you want to manipulate. It's static, which means it lives outside the Java heap. Java doesn't touch it, doesn't move it, because if you pass this memory location to native code and the memory is moved by Java, the native code now has an incorrect reference. So this memory must be static. Java must never touch it. So it doesn't. It's completely separate. So if you've defined your heap to be at most 1 GB, you can go beyond in native memory because Java doesn't look at it. So be careful about that. You can allocate it and yourself, or it can be allocated by native code and passed to you. So you can either receive a memory segment which you want to read into or manipulate, or maybe a library requires that you pass some memory with some configuration that it reads into. So you can either create the memory yourself, or you can just access the memory that you've received from a library or an API. So either by native code or in Java. And how do you manage this? Like, how do you decide where the memory is put and how it is cleaned up? Because we're used to not having to think about memory inside of Java. But in native code, this is often not the case. So how does Java manage that? Well, you need to allocate memory somewhere. And one of the key ways to do this is using an arena. And there are several arenas available. First of all, you have the global arena. The global arena allocates memory that is permanent. It exists for the lifetime of your program, the duration of your program. It never gets deallocated. So if you just want to create some memory and you want it to keep existing, this is what you use. What might you use this for? Maybe you have some initial setup code, right? You have like a Python interpreter, and the Python interpreter has to be set up. You're going to use it throughout your whole program, so you're just going to put it in global memory. Or maybe your large language model, you want to load the model once, keep it loaded always, global memory. Then you have auto. And auto is very interesting, because auto allows you to manage your native memory automatically, just as regular Java memory. So how does that work? Well, if you allocate memory, you get a memory segment in return, which references the native memory. And Java might not know if that native memory is being referenced, but it does know if you're still using this memory segment anywhere in your code. And if you no longer access it anywhere, if it's out of scope, if it's garbage, and the Java garbage collector garbage collects this memory segment, it can automatically see, okay, this memory segment is no longer being referenced anywhere in your code, so I can safely remove it. And that's what Arena of Auto does. So Arena of Auto will keep native memory in memory until you no longer reference it anywhere. But this is a bit of a lazy process because Java decides when it's going to do a garbage collection cycle, so it's not very proactive and you cannot control this to a high degree. And sometimes with native memory, you need to very explicitly state, I want the memory to exist now, and now I want it to be gone. So for that, you can use either a confined arena, which basically means I have some memory and I want it to exist so long as I keep this arena open and I only want to use it on a single thread. Or you can use a shared arena, which is an arena from which you can allocate memory and you can access this inside of multiple threads. So a confined arena performs slightly better but can only be used in a single thread. Shared memory can be used in all threads but doesn't perform quite as well. So how does that work, confined and shared arena? Well, this is how it looks. And if you've ever used database queries, you're probably very familiar with the try with resources statement. So if you create a confined or shared arena in a try with resources, any memory you allocate using this arena is automatically freed or collected as soon as your arena is automatically closed. So as soon as your try with resources ends. So if we go back to our QSort example, if this native array of data that we want to sort is used here and it's allocated using this arena, this confined arena, we can then use this memory to invoke the method, and then we copy it back to a Java int array, and then we're done. We are no longer going to use this native memory. It's already been sorted. We've copied it into Java world, so we no longer need it. Exit our arena, and the memory is deallocated. So I think both the auto workflow and this try with resources arena workflow feel very, very familiar to Java developers, and that's what's so exciting about this new API. Well, I intended to talk about that line by line. Right. So you do have to specify when you allocate memory what you want to allocate, what the layout of your memory is. And this is also important if you want to access a specific field or specific entry from memory. So there's several different layouts that you can choose from. What we've used so far is mostly integers because it's simple. So these are single values. If you just want to allocate 1 int or 5 ints, that's just a value. So you have an address, which is well, it's a pointer to some place in memory, which might be one of your own opcalls, for example, or one of your own allocated memory segments. You have your primitives, so your ints, your doubles, floats, etc. And then you have sequences. So a sequence layout specifies that we've made space for a certain element, but it's repeating a number of times. So this is what an array would be in native memory. You can create a sequence layout that explains, hey, I want to allocate memory that fits 5 integers. You do that with a sequence layout, or access memory with the layout of 5 integers. And then you have structs, which is what I talked about before, how we have 2 separate return values. Structs is just a group of different individual properties, very similar to what a Java plain old object representation would be. So to define that, you use a struct layout, and then you can just pass what members exist inside of the struct. And then finally, you have unions. It's pretty niche. You're very unlikely to run into them, and it's kind of a feature that Java doesn't have, so I won't waste too many words on it. To manage structs, right, you have complex data types. You need to tell it what members are inside of the struct. So this struct might have an integer called length. Then it might have some padding, so some unused space, and then you might have a character pointer to some character pointers. So this might be a custom string data type, where you first have the length of your string, and then you have the individual characters for your string. But because an address has to be aligned on 8-byte boundaries, a little bit of padding exists. And this gets into somewhat of a complicated topic, so it can be a bit of a hassle to manage this. Luckily, Java does automatically manage padding for us, so we usually can leave out padding, and it will understand that if you have a 4-byte value length followed by an 8-byte value characters, that it will add 4 bytes of padding in between. So you don't have to think about this too much. But still, this is quite a headache, right? Like having to define all of these memory layouts. You know, you don't have to write C or C++ code, but this is still a bit of a hassle. So is it really that easy to call in a native code and use all of these fun libraries or talk to the operating system? Well, yes. Because, and I promised you there would be something interesting here, we have a tool called JExtract. You can find this easily online, download it from the OpenJDK. It's a command line tool where you can pass in a header, which is a function definitions of a native library, and it can automatically generate Java code that binds all of the functions and data types and memory layouts that exist inside of this header. So what does that look like? Well, you just pass a location to a library that you want to use, and it will automatically load this library. So this is like a DLL file, or in Linux, an SO file. You tell it where it should write the resulting Java code to. You need to tell it where it can look for other headers that might be referenced from this header, your target package, and then the file that you want to generate bindings for. So let's say we want to call some Python code from Java. And I don't mean like convert the Python code to Java and run it in our virtual machine. I mean, Python's reference implementation is called CPython. You can actually use it as a library and just execute Python code, because there's a Python header file called python.h, and we can generate some bindings for this. So we tell it where our Python library is located. In a Linux system, it would be stored there. And you tell it where the other headers might be located, and then you tell it generate some bindings for the Python code. And then what happens? You have some Java code, and it generates somewhere, wherever you specify, some source files that bind this Python header. So it created a class called python_h, and this has a few functions that you can now just call into as if it was regular Java code. So to execute a Python script, we first initialize the Python runtime. Again, this is generated code, so I didn't have to hand write this. It was generated. It already exists. Just write pyinitialize. You can find this in the documentation of Python's official documentation. And then, of course, we have to create a script which we want to execute. So here we create a little Python script as a Java string. And what we want to do is, of course, we need to make sure that the string exists in native memory, because we cannot pass Java objects to native code. So we allocate some native memory, copying over the characters from our Java string, just like this, using our custom arena so that we deallocate the script after we no longer need it. And then you can just use a standard Python function called pyrun simple string flags, where you pass in the script, and this will actually run the Python script using the official Python runtime and finish, after which we just finalize and exit. And just like that, you can call Python code from Java. And I didn't have to write any custom binding code here. All I had to do was import this generated Java code using the JExtract tool, and then you can just use it as if it was always written in Java to begin with. So that's pretty exciting. But I have one more example that I want to show you before I send you all on to the next session. And that's llama.cpp. So there's a lot of exciting native libraries in the AI space. And the reason why they're written in C or C++ typically is because they have to interact with the hardware, with the GPU. They need access to drivers. Again, very difficult to do in a language like Java that's very cross-platform. But let's say we want to use this in our Java project to run a language model, run some generative AI. Well, what does that look like? Well, here's my tiny little bit of live coding for you. What I've done is I've generated all of this code. It's a lot of code, but again, it's generated using the Llama CPP library. And then let me see if I can bring it into presentation mode, by the way. Should be here. There we go. Now what we simply do is there's this AI model that I want to use. We have a little prompt here that starts with explain in a short and exciting way. Why? Well, this is awkward. That's not really the prompt I wanted to go for. Anyway, why Java developers should integrate libraries with the foreign function and memory API. We generate at most 2048 tokens just so it can give us a nice long output. And then we can use the Llama CPP API. So this is based on their example code. It's almost identical. There's quite a lot of code, but you know, that also means you get quite a lot of control. So first we specify a model. We're loading all of it on the CPU because I'm running in WSL. Can't really use my GPU. But otherwise it would be able to. Then, hello. Thank you. Then we actually load the model. And here you can see we're just allocating some global memory where I'm putting the path to the model just because I'm only going to be using this once. It's just a string. It can stay in memory. We load the vocabulary, which allows you to convert your text into tokens that the AI understands and also transfer the output back into text. Then we have some code to initialize the prompt. So here again, we're allocating a bunch of global memory, as you can see. And then we can tokenize our input prompt so that the AI can go ahead and use it. See if there's anything else of interest here. It's also generated functions from modifying the structs in this library. So there's a Llama context parameters configuration object that you can use. And JExtract has generated some functions for us, which allows us to pass in some memory and then modify the field called nctx. So I think that's the context size. And then we can just call that and then put in our value. We can do the same to configure the batch property. So it generates functions for defining and setting all of your struct properties. There's a bunch more of that stuff going on. And then finally here, we're creating a memory arena here because now I'm executing. I've set up the language model in global memory, but if I want to send in a whole bunch of prompts, I don't want all of that to be in global memory because that just means you keep on allocating more and more memory for each allocation. So now for an execution, we're going to put it in an arena so that it gets cleaned up. And inside of there, again, this is just based off the sample code. If you're interested, you can ask me later and I can share like a GitHub link or something. And then eventually we're just processing and telling it to give us the next token, which we output to the screen. And then here I've written some code so it doesn't make the lines too long, etc., etc. Well, let's just run it and see what happens. So we get a bunch of standard output from the library. And here we go. Explain in a short and exciting way why Java developers should integrate libraries with the foreign function and memory API. What does the AI think? Well, Java developers should integrate libraries with the foreign function and memory API because it unlocks massive expansion of their capabilities, allowing them to build truly powerful, scalable, and complex applications. FFmpeg provides a way to dynamically manage memory, allowing developers to create highly optimized, efficient, and potentially even invisible memory management, leading to significant performance gains and the ability to handle truly massive data sets. It's a key to unlocking the next generation of Java applications. And again, this is generated real-time, token by token, directly using the library. Here you can see it kind of go in real time on the CPU, and it's directly integrated into the Java program. For very heavy models, probably not the way to go, but you can use this with everything. And it's really easy. So any native library you want, generate your own bindings, just use it. And at the end of the day, you never have to be worried about your choice of language again, because now with Java, doesn't matter that you're using Java. If there is some library and you want to use it, some operating system functionality and you want to use it, you can. It's up to you. So that is the key takeaway. And I think if I can exit my presentation mode and go back real quick, well, this was in case the demo wasn't working. Before you go, I hope you learned something. And if you want to talk more about it, I'll be at the Chill It stand. If you haven't visited yet, we have waffles that you can get, other snacks. And we have a really, really exciting hot sauce challenge where you can play a little game with us. There are a bunch of games to choose from. Talk to us, and if you lose in this game, like for example, you get a question wrong if you choose a question and answer game, you have to eat a little chip with some hot sauce, and it gets more spicy each time. It's really fun. So come and talk to us, say hi, and I'll be there, so let me know what you think, ask any questions that you might have. I hope you learned something, and I hope that you'll keep this in the back of your mind, and if you see a native library, or a library really in any language that you want to use, you'll remember that using the Foreign Function and Memory API, it's really in your own hands, and it's not really that difficult to get started with it and integrate it into your own program. That's been my talk. Thanks, guys, and enjoy the conference.